Hello, GTC 2022. I'm Andy Lin, Vice President of Strategy and Innovation at Mark III Systems, an NVIDIA NPM Elite Partner. Thanks for joining us today for Making Multi-GPU Simulation Accessible to All with DGX A100 appliances in partnership with CPFD. I'm honored to introduce our guest speaker today, Peter Blazer. Peter Blazer is Vice President of Operations at CPFD. He'll be walking you through today's session. Peter?
Thank you, Andy. And hello, everybody. What I'd like to do today is to begin by introducing a multi-GPU simulation technology. We'll be specifically speaking about ours, but the application can be easily transferred to other multi-GPU simulation technologies. I'll talk briefly about multi-GPU speedup and why it matters. And I'm going to hand it back to Andy at that point. And he's going to be talking about how to practically access multi-GPU simulations using the NVIDIA DGX A100 systems. So with that, let's go ahead and get started. So a bit about us here at CPFD Software. We're advancing multi-phase simulation and technology for fluid particle systems. These are systems like fluidized bed reactors, and I don't actually expect most people here to know what those are. But no, they're used everywhere. And we'll talk about that in a moment. So we've embodied our technology in a product called Barracuda Virtual Reactor. It's a software product that models the hydrodynamics, that's gas particle motion, the thermal behavior and chemical reactions in industrial units. And this is physics-based modeling that's accelerated first on the GPU for almost a decade now. And then last year, we released our multi-GPU simulation parallelization version. And so the way it's typically used is for existing units that improves the reliability and performance of industrial units that often operate, I'll say 24/7 for maybe 5 years on end. So any small change to throughput to uptime makes a huge difference. It's used to look inside virtually, determine the root cause of phenomena, perform virtual testing of alternatives before going and implementing on the unit. In the process, invariably, other optimization opportunities are identified. And for companies that are developing new technology, commercializing and scaling, they're able to explore a broader base during their R&D and then more rapidly commercialize and scale the best ideas, taking to market much quicker. So we work in a variety of industries, from oil refining, petrochemicals, materials. I'll go through these briefly. And if you don't know the industries themselves, that's okay. You see use the products on a daily basis. In oil refining, this is an example of a process central to many refineries called a fluidized catalytic cracking unit. It makes the gas that goes in your car. Petrochemicals, polyolefins, polyethylene, polypropylene, dehydrogenation processes. These make your plastics, protective equipment, clothing, recycling of plastics. Gasification makes chemicals and energy. And traditionally, this has been coal and petroleum coke. And we've seen a huge transition to renewables and even waste to products. I'll get through a cool example in a minute that goes through a conversion process for taking municipal solid waste and making jet fuel. And so this is one area where the software is used. Materials and chemicals. This is a preheater tower for a cement calcination unit. This makes the cement that goes in the roadways. But other materials and chemical applications include the materials for solar panels, pigments, and transitioning these toward net zero emissions. Power generation for your electric vehicles, whether it's the generation of power. Here's an example of a circulating fluidized bed combustor unit, or the emissions control systems. And a lot of these are transitioning from things like coal to renewables. And those are some of the traditional industries we've served over the years. Our biggest growth area right now has been what I'll call the sustainability, renewables, decarbonization space. Everything from chemical looping combustion units, infinite recycling of plastics through what we call chemical recycling or advanced cycling, and all sorts of decarbonization applications. We work with research groups on basic fluidization, how the fluid particle behavior develops. And we're moving to three-phase systems, ongoing research and development for vapor, liquid, solid systems, and more. So with that introduction, this is award-winning technology. We've been honored to receive several highly commended designations from the IChemE in recent years for projects with our clients. Just over a year ago, we won Best Software Technology from the Hydrocarbon Processing at the Hydrocarbon Processing Awards. And this is largely in part to being able to achieve things using a parallelized code built on the NVIDIA CUDA technology stack, the hardware and software. I mentioned we came out with single GPU parallel almost a decade ago, and most recently came out with our multi-GPU version last year. And what we've seen has really been tremendous. Speed ups of over 400 times over serial on a single workstation. Compared to the CPU on a DGX Station, for example, the 4 GPUs are running 400 times faster in some cases. It's been truly phenomenal. So what I want to talk about for just a moment is why does speed matter? And it might seem a little counterintuitive, right? Faster is better, but how and why? And it's really surprising to me when we started looking at what people were doing with this technology. The obvious outcome is faster results and more cases simulated. So consider a more modest speed up, 150 to 200 times. So what does that mean? It means a week-long simulations done in an hour, or flip that out on its head. 150 to 200 simulations could be done in a week. And what this means is now the ability to broadly explore a design space or an operational space is hugely expanded, enabling things like machine learning on exploring out that space, much more possible than before. The other thing it means is that fewer physical tests are being performed. We recently spoke with a client who develops technology for refining applications. And what he said is that, in the past, they'd come up with a handful of ideas, maybe 2 handfuls, 5 to 10 ideas, do some analysis, come up with their best, maybe 4, send them to physical testing, and then commercialize what they think is the best to scale up. Now they explore a much broader space on the computer, take 1 or 2 designs, send that to physical testing, and build, release their technology based on that. So all of a sudden, they're exploring a broader space. Their testing costs have been cut in half, and they're bringing technology to market faster. So that's sort of the first outcome of speed. New technologies are brought to market faster at lower cost, and that's maybe the most obvious one. Let me take another one here, and actually let me pause this. I'm going to talk through sort of a historical model for a moment. So here is an FCC regenerator simulation. So this is a refining application that we did back in 2012. In fact, when we ran this back in 2012, it was probably the first full-scale thermal reacting model of this type ever performed. And just to give you a feel for the scale, let me back this up just a moment. You're looking at about 120 feet tall here, 70 feet tall here. This vessel has all sorts of internals, and the client had a problem. So let me play this and talk through a little bit. It was not possible in 2012 to run this in a single model, not even close. So we broke it into 3. The first model, and their problem was some temperature excursions at the top of the unit. So the first model looked at the lift line and said, maybe non-uniformity here is what's causing a non-uniform temperature, what's limiting us. So we ran a model of it. We broke this into a model, looked at the flow, and sure enough, there's a maldistribution of the gas and particles as it starts to come up this lift line. Is that what's causing the problem? We took the output from this. So here's the transient behavior as it's flowing out the top, integrated that over time, and then use that as a boundary condition to a second model. We hope this second model, model 2, would be the final model. It included the flows entering the unit. It broke down into 17 different arms, each of those to distribute the catalyst through the unit. Each of those arms had a bunch of holes. And what we found is this model would take forever. It actually was going to take 3 years to complete. Kind of the client didn't want to wait for that. So what we did is looked at the flux through each of these arms, mapped that onto a smaller model of just now the top unit, mapped boundary conditions, incredibly tedious exercise. Put the flow of the gases and the particles from what we learned from the first model, map to the second model, go into the third model, and begin to look at what's happening. And so here we're seeing the catalyst particles moving through the system, and you see that, okay, the internals are having some effect. Deeper analysis, there's some bypassing of the gas and the catalyst, and even talking about it's somewhat exhausting, right? This was a very long process. The Model 1 ran in 2 days. That's acceptable. Model 2 wasn't going to work at all. Model 3, the fast one in 2012, 300 seconds of simulation were required. It took 2 months to achieve that. And eventually what we see here is we look at the temperature as the simulation run. Yeah, we're predicting where the hot spot is. We're predicting the limitation and the effect on emissions. So it was a success, but I'm really glad it's not 2012. So what we did is we ended up doing a benchmark now. We didn't have the original model anymore, but what we found is, okay, this is a plot, and it's a log plot. So look at that right away. Model 2 would have taken about 3 years to complete. It was getting about 0.27 seconds per day. Model 3, smaller, fewer cells, fewer particles. It was getting just under 5 seconds a day, ran about 2 months. So we can benchmark that against a couple of recent projects that we're running right now on the DGX Station A100. Here's what we found. This first one here, recent project number 1, had about the same number of cells as Model 3, about the same number of particles as Model 2. It was getting 550 seconds a day. What that means is it would be complete in 13 hours. Right? We're talking years and months before, 13 hours. Now, realistically, what we do is we run finer models. So here's another one. Instead of something like a few 100,000 cells, it's at about 2 million cells. Instead of a few million particles, it had 43 million computational particles, which our clients are going to know what that means. It's a bigger model. So we ran that on 4 GPUs on the DGX Station under my colleague's desk. It ran 146 seconds a day, meaning it was done in 2 days. Think about that. Comparable models to what took months and years before are now done in 12 to 48 hours. And so this is the impact. We don't run those models anymore. We run higher fidelity models. So speed has another outcome here, right? Larger domain. We don't have to deal through all the tedium of breaking this up into 3 different physical domains. Finer spatial resolution, more detailed physical models, more complex chemical reactions. And this is common today because of the speed produced by the GPU simulation. And the third sort of case of what we're seeing is as we're making these more complex models, we're finding it's possible to run simulations that were physically impossible to run in the past. Let me give you an example. This is from a company called TRI. We've published this elsewhere. They developed and commercialized a trash to jet fuel technology. This was highly commended by the IChemE, International Chemical Engineering Society, at their 2020 Global Awards in the Process Automation and Digitalization category. And what we reported last year's GTC is that a 1500x speed up was shown since 2009. And so you can find that. We have playback of that available. Now, here's the thing. The types of models we're running now, not physically possible to simulate in the past. And really what this GPU, multi-GPU technology is doing is it's making what was previously impossible possible and really solving some of our planet's toughest sustainability challenges in the process. So with that, kind of wrapping up the story, we've been really excited. Our clients have been really excited about multi-GPU simulation. It's game changing. And we released it and found out that, you know what, a lot of our clients weren't sitting on multi-GPU capable machines. They didn't have the hardware. And so what I'm going to do here is transfer control back to Andy and have him talk about, what our clients have been able to achieve now through a very accessible solution. So Andy, yeah, go back to you.
All right. Thank you, Peter. Really appreciate it. So I'm going to spend a little bit of time talking about Mark III and how we partner tightly with NVIDIA and CPFD. And our mission all around this is really to make multi-GPU simulation accessible to all through the NVIDIA DGX A100 appliance, both in terms of the server, if you prefer data center, and then also under your desk as well. Not everyone has access to a world-class data center. We know in working tightly together that many folks do some incredible simulation work with just equipment under their desk. So there are a couple different options. But first, a little bit about us. 25 years, NVIDIA NPM Elite Partner. Really anything that you need in the NVIDIA stack. Of course, simulation and visualization, but also AI, ML, HPC, et cetera. I know those aren't in scope today, but these are all things that we can potentially assist and help with. And at the end of the day, our job is just to make it accessible and simple for folks to immediately start diving into the software and start using it to fundamentally reshape their businesses and solve their problems across all types of industries. We've had the honor of working tightly together with Peter and the team for a few months now, and we've been amazed at just the applications really across different verticals and across different industries, and know that we're truly just getting started. There's a lot of different models that I'll talk about in a little bit on ways that we could potentially all work together, but whether you're talking about pre-integration or it's laying on site. But like I said, first I wanted to talk a little bit about the architecture and some of the unique things that DGX brings to bear, specifically with multi-GPU simulation workloads with CPFD. So you guys have probably seen this slide multiple times, just being at GTC and talking within the NVIDIA ecosystem for some time. But I think it really is important to sort of reemphasize. DGX A100 is truly the universal system, not only for AI machine learning, but simulation and all accelerated workloads. And the thing that's amazing about this platform is you can put in up to 8 A100 GPUs inside with 80 gigs of memory each. And with this platform, you can basically parallelize not only simulation workloads, but different types of workloads that may come into scope as you go. And I think this is really important because it gives you a lot of versatility and it gives you a lot of ability to run, for instance, different types of simulations all in parallel if you like, or you can use many, many GPUs all together if you have very, very large simulations that we'll touch on in a little bit. But the versatility of this platform is extremely important. And as with anything, the DGX A100 server, like I'm showing you here, is a data center class platform. So if that's something that an organization needs, it already has all the capabilities and all the uptime and all the robustness that allows you to enable that function. And then you also have the NVIDIA DGX Station, which we found to actually probably be a little bit more popular with folks initially at this point, because oftentimes we know that if you're not even running, for instance, multi-GPUs out there today, you have the ability to take this and actually even slide it in under your desk and immediately start going with up to 4 A100 GPUs. Really an amazing thing. If you look at some of the other industries out there, really, I mean, this is what we see as sort of the dominant platform in this particular space for all forms of accelerated computing, including simulation. Breaking the data center barrier. It's amazing to think that you can have a supercomputer that's super quiet that slides into your desk, but that's exactly what we're seeing out there for folks that are starting to use this specifically to run Barracuda Virtual Reactor in a multi-GPU scenario. And then just to reinforce some of Peter's points around performance, and I think some of these may be even a little bit conservative to a certain extent. No matter if you're running small simulations or large simulations, you're going to see some incredible speed ups, which will have a direct impact on how many simulations and how many iterations that you can actually run and how many ideas you can basically explore out there. If you look at small simulations, we've collectively seen all together that oftentimes, with these small simulations, you can't even get above one or even two A100s. You'll completely max it out. So what that means, if you have, for instance, a station where you have 4 GPUs, it means that you can potentially run up to 2 to 4 simulations in parallel, which allows you to get significantly more done, to simplify it, than previous. Now, if you have large simulations that do require multi GPUs, right, you can see really the huge performance improvement. Some of the numbers cited were 50 to 400x improvement for these large simulations that do require multi GPUs. So, what does this mean essentially? Small simulations, large simulations, you can get exponentially more work done. You can explore exponentially more ideas, and this is all enabled through the DGX platform from NVIDIA. And then lastly, what are some of the options out there? And this is something that we put together in partnership with NVIDIA and CPFD to make this accessible, right? Multi GPUs have already made certain types of simulations accessible that weren't accessible previously. How do we make the actual platform and get you going faster than ever? And this is how. We have a couple different options on actually how you can acquire this. We can either ship a DGX A100 station or server on site, and we can help you actually integrate it. Or we can actually pre-stage and pre-integrate. Both CPFD and Mark III have our global headquarters in Houston. So we have a collaborative partnership to actually enable this to happen. And this is something we've already seen a lot of interest in immediate client success, even in the last few months. And we're really excited about the year ahead. So if you have any questions, feel free to reach out to Peter and I around these types of topics, exactly on how we put this together. But in the nutshell, it's how do you make multi-GPU simulations accessible? This is a big part of that holistic story. And with that, that's all I had today. I wanted to thank you. Peter, any last words before we sign off?
Yeah, thanks, Andy. It just hit me as you're talking that, sometimes you do these talks and it's a concept for the future. And this is here today. Since the few short months we've been working together, we've already deployed this at multiple clients. Feedback has been incredibly positive. So thank you for working with me on this today and for just being a great partner. I want to thank the audience for joining us for this. And if you have any questions, please reach out to Andy or myself, and we'll be happy to talk to you.